Hello. Today I have the task to introduce our project ReCEMENT to you. And then it's about regenerating materials and end-of-life products for reuse in cement and concrete industry. We are trying to address topic number 4, recycling and reuse of end-of-life products. And then our transnational consortium has 4 partners from 3 different countries. 2 of them are EU countries, members already, and then Turkey is an associate member. When we look actually closer at our consortium partners, from Turkey, we are the Sabancı University, and then we are the consortium coordinator. There's also Professor Bonder from Özyeğin University. So both of us are from university backgrounds. And then from Slovenia, we have, again, 2 partners. One of them is the Vila Stefan Institute, a research institute. And then the other one is University of Ljubljana Geology Department. Our Romanian partner is University Polytechnica Bucharest. And so this is actually our whole team. When we look actually at the structure of our team and then the strength of our team, first of all, each team member has really an established expertise in our subjects, in the subject of our project. And then when we actually structured the team, we actually made sure that we can actually have a substitute for each team's strength. So we looked at the strength of our team, and then we make sure that another partner in the team can really substitute for for that purpose if there's actually any delays or any mishap that's happening in one of our team members. So, and then the most important part of the team, of course, that most of the team members know each other for more than 10 years. And then some of our friendships are dating back about 25 years. That actually was already a strong friendship as well as trust among the team members. And then we are now working together. The objective of our project is to activate suitable end-of-life materials for pozzolanic-like reactions as cement replacements, as an organic binder. I'm assuming that most of you are not very familiar with the cement jargon, so therefore let me just introduce some of the terms that I used in the slide. First of all, most important part is, of course, the pozzolanic reactions. It's a type of reaction that the ancient civilizations like Greeks and Romans, Egyptians, Ottomans, and Chinese used about 5,000 years ago. And then they used actually unstable aluminum silicate and then mixed it with activated and soluble calcium sources in a strongly alkaline slurry. And then during the reactions, this thick slurry, this paste, converts into a solid material that can load tons of load that's actually loaded on it. So, and then the beauty of the pozzolanic reactions is, of course, it utilizes already available resources. When you look at the earth crust, about 50% of the earth crust are made out of cations like silicon, aluminum, calcium, and then these are the main ingredients of the pozzolanic reactions, as it was indicated before. And so, but then most of these things, except for lava and for certain phases like zeolites, they are rather stable. So there's a need to make them first unstable, like the Romans used, for example, lava from volcanoes because they were rapidly frozen, glassy aluminum silicates that were already unstable, and then they were really very strong against the strong alkaline solutions. So the strong alkaline solutions could attack it and then start the reaction. So we need to actually bring available aluminum silicates in this end-of-life products into a state where they are unstable against this, strong alkaline solutions. When we look actually into the composition of the end-of-life materials that are produced in large quantities, of course, it also reflects the same compositions or similar compositions like in the earth crust, because those are the most available and inexpensive resources. So, and then when we also look into things that are left over from many of our activities in industry, like mine tailings or the materials that are left as the remnants of extractive metallurgy or refinery, we also see that the compositions of those are also very close to the composition of the earth crust. So availability is there, we have to find a way to activate them. And then, well, we realized that actually these ancient civilizations could activate it about 5,000 years ago. So why can't we not do the same thing? And then at those years, they only had to their usage wood burning. So that will actually maybe 900, maybe 1,000 degrees and not maximum more than that. So we should be able to do it also at low temperatures. And then help in this way, maybe also reduce some of the carbon dioxide that's emitted from the cement production today. Today, the modern cement is the so-called ordinary Portland cement. And then production of the ordinary Portland cement causes about 8% of the carbon dioxide emissions on Earth today. So by really using this end-of-life products and activating them at much lower temperatures than what cement industry uses today, we will also be hoping to reduce some of the carbon dioxide emission that's actually being done nowadays. So in the project, we divided our activities into several subsections, and then these are, first of all, locating these end-of-life products and then assessing how big they are and then what they have. So, and then we have to collect samples from them. We have to analyze the samples and then identify the phases that are in them, look into the phases and then see if there are any activatable and useful minerals within these end-of-life materials that can be activated for pozzolanic reactions. And if this is possible, then we have to activate it and then blend it with ordinary Portland cement to certain ratios and then see if they can be actually used as an inorganic binder along with the Portland cement, replacing some of it. And of course, if this is possible, then we have to look how good this new blended cement is, that where we utilize the end-of-life products, activate end-of-life products, and then assess their durability as well. So since this is going to be a public data that's going to be shared, and then since most of our results are not shared as literature or as manuscripts, I will actually be giving you rather concise and refined version of our results so far. First of all, of course, we did locate where we have useful materials, so we created interactive maps. And we collected samples from these locations. So we collected 6 different types of materials that are all either at the end of their useful time or they were created as waste and causing landfills. We analyzed these samples with all the available techniques that are available at our respective institutes. We even quantified the amorphous content. Then we look at their thermal decomposition behavior and see if they were possible to activate. And then those which were possible and suitable for activation, we created unstable aluminum silicates out of them or unstable calcium sources out of them. And then we tested their pozzolanic activity in saturated calcium hydroxide brine. And once they gave actually good pozzolanicity, that's what it is called. When they are reactive, they have good pozzolanicity. And then we mixed them with ordinary Portland cement, hybridized them, and now we started testing them for their compressive strength, and then we are also doing the durability test on them. So the 2 maps here, one from Turkey, one from Slovenia, are the maps that we created. So all these different colors and then different location indicators, you can just click on them and then see what kind of deponey or mine tailing or end-of-life material they're stored. And then you can actually see if this is really valuable for us. And then, so these are the locations, not all of them, but then these are some of the locations that where we collected our samples from. Slovenia did the same thing, and then Romania is also doing the same thing. So these are 2 examples only. So the 6 materials that I was talking about, one of them is copper mine tailings. And then, so we do have 2 we have many locations, but then 2 of them we get samples from and then investigated. And then they do contain various aluminum silicates, including clays and feldspars. Then we do have 2 red mud samples, which is a problematic material because it's a mud, which is extremely high alkaline pH environment. So, and then we do have construction debris from already taken down buildings as well as road constructions, and then we investigated those as well. And then they're already cements, and then the fillers in them. Then we have rejects from the ceramic industries that are the aluminum silicates. However, the problem with them is that they are sintered and now they are very stable. So we have to find out a way to activate them for pozzolanic reactions. In Romania, there are fly ash deposits, huge amounts of them. And then fly ash is already known to be a good cement substitute that you can actually replace. And then we are trying to actually also incorporate that into our project. And of course, we do have a marble dust wastelands that are all over the country. And then, of course, they are the marble dust that's generated during fabrication of marble slabs that are all deposited on very useful agricultural land and then basically killing that agricultural land. So once we can actually remove them and then use them in some other industry and make commercial products out of them, we will also open up the agricultural land back for food production. So when we actually look and analyze these end-of-life materials, we look at what phases there are and then which phases are activatable, or at least we think activatable, and make a huge table out of them. And then it's an ever-increasing number. And we look at how much their content is in these end-of-life materials, and then check if it can be activated. Once they're activated, then we put them with the hydration reactions with ordinary Portland cement. And then as you see here, we are doing in situ electron microscope studies, in situ X-ray studies to see how the hydration processes are now continuing. I'll speed up a little bit. And then, of course, nothing is not finished. So there are challenges ahead, and then there are opportunities that are due to these challenges. First of all, the 2 red mud samples that we have are difficult to mix with ordinary Portland cement, but I think there's a hope. We are trying to destabilize feldspars. That's the large portion of the aluminum, but they are very stable. They are pre-clay. In 5 million years, maybe they will convert into clays, which are activatable, but we're trying to do it not in 5 million years, but maybe in 5 hours or so. We are working on it. Probably are tedious, it's taking a long time, and then hopefully we'll do the electron microscopy, in situ electron microscopy, and then in situ XRD, and that will be a strong contribution in this field into the scientific literature. And then red mud itself might be a calcium aluminate cement, specifically the one in Turkey, contains large amounts of calcium aluminate hydrate, and that will be very useful. How did actually ReCEMENT help to us? Well, first of all, each team was active already in the fields of our project. And then we shared already previously experience through guest lecturing in respective campuses, which is traveled around, but these were funded through national funds or through bilateral funding schemes. With ReCEMENT, we brought this accumulated but dispersed experience into action in the scheme of one coordinated project to make actually possible recycle and reuse of end-of-life materials in cement industry. And by doing that, we would like to actually reduce the stress on the environment that cement industry is causing by reducing this CO2 emission that they're basically producing every year. They're really creating 8% of all carbon dioxide on Earth that's created by industries. We are trying to reduce the need for new raw materials so that we can actually save some of our landscape. We would like to actually reduce landfills from EOL by just taking them out from there and then putting them back in the industry and then creating a commercial product out of it. And then with this construction debris, we just realized that we can activate them very easily at very low temperatures. Then they become, again, construction material. And then that becomes like an endless cycle of making a building when it's done, taking it down, and then reactivating it and making another building out of it. So that would be perfect. So with this, I'd like to stop here and then entertain your questions if you have it. Thank you very much.